Hello everyone, my name is Mateusz Pusz. I'm the Chief Software Engineer at EPAM Systems, and thanks to that I am often working with the large code bases and large-scale projects. Also, being a C++ trainer and a consultant, I often being asked by my customers what is the best way to export their libraries, their products, and how to use dependencies and how to import dependencies of their projects in C++. To answer those questions, I spent quite a lot of time exploring the tools that are on the market right now. I ended up with such a set as on the slide title, so with Git, CMake, and Conan, and we'll talk about them today. First, I would like to state that I am in no way connected with Conan team, so they don't pay me for this. I just found it really nicely working for me. So I decided to share that knowledge with you. Second thing for today is that we have really a lot of material to cover today, and only 60 minutes. So if possible, please postpone your questions until the end of the presentation, and if time will allow, I will answer those. Okay? So let's start. Let's see what we have right now on the market for C++. Do we have some standardized toolsets already? I think that when we are talking about the version control system, every one of you is thinking about Git right now, yes? This is a standard that is being used by nearly everyone. For building of our projects, we use CMake. And this is also quite a standard, maybe not the best one, but it is a standard. And we have to agree with that because most of the project can be built with CMake right now. For package management, we have none right now. That's being standardized and used by everyone, or most of the libraries. My personal note here and basically request to you, please do not partitionate our C++ development environment even more. We already did it, and it's right now being somehow converges to those tools in the table, and that's good. The thing that you will maybe find some tool that works in one way better for you, doesn't mean that it works in all the cases. Some tools are better in one things, but are worse in many other things. There is no game changer on the market right now. By game changer, I mean what Git did, for example, with Subversion and other version control systems some time ago. This is a game changer, yes? At least as long as such a game changer will not appear on the market, it will be good to use those tools for our projects to make it easier for everyone to use and reuse your libraries and not have to fight with 5 different building systems, one's trying to build your own library, for example, with dependencies. It turns out that, at least it's my opinion, it seems that Conan is answering the package management area here. It's really good, and it, as my client said on the last training I did, it just works. And I think that's the best recommendation for this. In C++ world, if something just works, it's not that obvious, and it's really welcomed here. Okay, so let's analyze how we handle dependencies in our C++ projects. First of all, it's common to use something like an external or third-party subdirectory in our project, and we copy-paste the dependencies code there, use CMake add subdirectory to include it and build it, yes? I assume that you've seen such things like this being done in C++ projects. Another point is you can use Git submodules to do exactly the same. And you can also use CMake external project add command that basically will download the sources for you, but still it's being added by add subdirectory with CMake. Those 3 approaches has some problems that I will answer on the next slide. Fourth point here is you can always download, build, and install each dependency by yourself and then look for it with find package. We often do this, for example, with gtest or maybe with boost, that we are just installing it in our file system and use find package to find it. Another point here is people try other languages, package managers like NuGet, like Maven to do C++ stuff. Those are really good package managers, but not for C++. They were created with another language in mind. and they do not work right for us. The last point here is the rise of C++ dedicated package managers on the market. I think that the best example right now is Conan, and we'll talk about it today. Why not add subdirectory? Let's consider such dependencies. We have some lib-a here, and it uses two dependencies, boost 166 and gtest 180. By this arrow, I mean that the boost is exported in lib-a interface, and by this I mean that it's only private dependency of our project needed for unit testing, so it's not exported with the package when it's installed. Yes, and it works fine for this case. However, we may find out that we have another library, lib-b, that uses different boost version, different gtest version, and it also has OpenSSL that's maybe not exported outside of our lib-b library, but still used by it for in a package that we'll distribute. And it still works fine. However, when we build right now the application that uses both of them and also uses gtest but another version and uses different OpenSSL, we are starting to having problems here. Yes, especially that this lib-a and lib-b export some headers, for example, file system or other headers from Boost in their interfaces, and right now have two different kinds of interfaces and different libraries of the same package from different versions. It doesn't scale, yes, and it's really hard to manage. So we'll try to answer other points, especially how to make it right with Conan later on. But first we have to talk about CMake. CMake is not a build system, it's a cross-platform C++ build generator. This is a typical workflow that we are using with CMake. We can configure CMake script, we can build with CMake, we can test with CMake, we can install with CMake. You can see that we don't have to use any makes or other build system specific commands here, even for Visual Studio, yes? The important difference here is that some generators allow us to specify build time during the configuration stage. This is the case for GCC, this is the case for Clang, for example. But for example, for Visual Studio generator, we'll provide those in build, test, and installation phase, and not during the configuration phase. During the configuration phase, we don't know if the client will run debug or release for us. And this is the important difference here, and it affects how we have to write our code in CMake, as you will see later on. There is something called modern CMake. I will not repeat that. This was really great, introduced by Daniel Pfeiffer, the author of CMake. So I recommend going to this presentation and learning that. I will just point some important highlights from this presentation here. First of all, build flags don't scale. Every change in public flags has to be propagated upwards. By this I mean, for example, if you have information like include directories in some dependency low in the hierarchy, you have to provide the same include directory up for all the projects here in order to be able to find these header files, yes? It doesn't scale at all. If something changes in your dependency because there is a new version of this dependency, you have to modify all the CMake files of all the projects using this dependency in order to find those header files, which is a really big problem in scaling of our large-scale software application. Also, different targets may require different conflicting flag values. Let's, for example, consider such unique name like verbose. And one library can use verbose in range from 0 to 3. Another library can use verbose in range from 1 to 5. And how do you want to configure those two libraries with one verbose flags in your CMake files, yes? It's not easy. So modern CMake is about targets and properties, like Daniel said on the previous slide. What I mean by this? We create targets with following commands. We can create executables with add executable, and we create libraries with add library. The library can be shared, can be static, can be object, can be interface, or so-called library alias. Also, you might define something called imported library, which means that the library is not being to be built from sources. CMake just assumes that you have already binary, and will package this binary as it is with all the CMake configuration files. If no type is provided in add library call, then it's either static or shared depending on the configuration flag build shared libs of CMake. So what I can suggest here is using those specific add library calls for dependencies of your package, like you having 3 different static libraries that are being linked into the package that you export as a library of yourself, of your company. And those should be probably static, and they are linked into one output library. And this output library can be either static or shared, and it's up to the client to decide. So this output library should not be provided either static or shared. It should be configured with CMake flags here by the client, how he wants to use your library that's being linked from all of those parts that you linked with, for example, static there. In order to make targets and provide those properties, there are target XXX commands. One of those, and most important one, is target link libraries. As you can see, the first argument of those commands is a target you are either creating or you are modifying with some attributes. And those attributes are provided in a list, but they have tags like private, public, interface. If those things that you are changing are needed by me as a package creator and by my dependers, then this dependency is public, yes? If it's needed by me to build the package, but the clients of my package will not see it and not use it, it's private dependency, yes? If it's used by the clients, but it's not being used by me during the build phase, for example, because we are using the header-only library, and for this we are not building at all, it's an interface. And if it's not needed by me and not needed by the clients, then we don't bother here. What's important part here is that interface and public dependencies are transitive, while private are not. So if you will create something as a public, for example, in your library, then all other dependers that will be linking with your library will know about it and will get those attributes in their own library. So you don't have to distribute those include directories up to the top of the hierarchy, because they will be imported transitively from the library with public dependency. Using CMake in an old style and leaves us with such a design of, this is the large-scale design of the modules in your project. This is from one of the projects. This is exactly CMake generated graph viz diagram from one of the projects I worked on. Basically, when I started to work on, they were using old CMake, and as you can see, that all packages depend on all packages because they have to have those include directories and other stuff being distributed up to the top of the hierarchy. It turned out even that one of the targets is totally not connected to the others, and everything links fine because of the linker magic in C++. When I refactored this, I ended up with something like that graph. We have strict dependencies here, layering of the modules that we use. It's much better. This one right now is connected somehow to the other parts of the library. And I also find out that it doesn't compile at all when I did this thing. And I had to introduce private loops here. Yes, these are problems in the design that I found out only with using proper CMake, because I found the problems in large-scale architecture of my project. And basically, these are these are problems, and if you are not agreeing, talk to John. Basically, it's really bad idea to have cyclic dependencies in physical design of your library. So I mentioned a bit about the alias targets that you can create for libraries. They are used to create so-called something that looks like a namespace in C++ for a library. This namespace probably you are aware of already if you are using find package in CMake. If you are doing find package gtest, it will return you something target called gtest, for example. This is exactly that. This is exactly what alias is using for us. It allows us to refer to the same library either finding it by find package or by just defining the package like this here. Yes, we are building a library and we are saying it will be used with this link here. So then, doesn't matter if you're using find package or this definition. In both cases, this one will compile because it will link correctly and will know what my company, my library means. Another really important point here are generated expressions. I know that the syntax of it is really, really not friendly, and I really don't like it, but unfortunately it works for specific cases and you have to be aware of it. The difference here is that those generated expressions are not evaluated during the configuration step of CMake, but they are evaluated later on, for example, during build or install phase. The use case for it can be, for example, this one. You can see here that we have if branch here for build type. If it's debug, we add some debug sources. And in other case, we add release sources to our library, yes? However, if you remember, this will already only work for GCC and Clang, because they know what's debug or release during the configuration stage. However, if you will work with Visual Studio Generator that doesn't provide any build type during the configuration stage, it will not work correctly for you, because you specify during build phase which type of the build you would like, and this thing happens during configuration. So you have to type such a generator expression in order to make it work correctly. So you say that you use config. In case if it's a config debug, then you use debug sources, and in other case you use release sources. And this will be evaluated during the build phase of CMake. The key point here is to never use CMake build type in if branch. Always use those generated expressions for CMake build type. Another use case for this wired syntax is when you are installing your package, or maybe when you are building the package, you are using the include directories that are located in your source tree. After the installation, users will use the include directories that are in include directory that's being on your installation target file system, yes? In order to make it work correctly, you say that your target include directories for your target foo are either in the source tree if you are building, or on the file system that you installed the software when you are after the installation phase. So when you are using the installed software. And with that, always your target will find correct headers for your project. This is the simplest example of the modern library. First, we provide information on what CMake version is needed to compile this stuff and configure stuff. Then we provide the project name and the version of it. The next phase is adding the dependencies for CMake. And then you are defining your package. To define your package, you basically define which files are being used for compilation. You define which compiler flags, I mean which versions, which features are being used. I'm not talking about the warnings levels here, to be explicit. I'm saying where will be include directories during the build and after installation. I provide this target link library in order to make this library work correctly with find package or not. And this is where I create this link, yes? As you can see, this is quite a lot of things being done here. This is a full-featured library file for CMake. And I didn't use set command at all in this file, and everything works fine, yes? Please avoid using custom variables in your CMake files because they only give you some problems. Like, for example, they are not case sensitive, or if you have typos, that will just compile fine, but will not work correctly. This is how I organize the files on my projects. Basically, I have one big directory that contains two subdirectories, sources and tests. In sources, I have my library that is being built and installed. It has CMake list file that can be built as standalone. I mean, just going to this directory and building will make this compile fine. And this one never changes the compiler warnings. It's a really important point here. You may assure that, for example, right now your library doesn't provide any warnings for your clients because you checked it during the CI phase. But in 3 years, when you have 10 new versions of GCC and Clang, maybe they will find some bugs or some problems in your code, will raise some warnings, And then the clients will have problems with building your application as a dependency, only because some warning was raised that they don't care about, because I assume you never, or rather not often, fix the dependency packages when you find compilation warnings there. So it's up to the client to decide which warnings flags should be set, not to you as a vendor that distributes the package. If you want to use it and to set some flags for your build, use it in this file that's being used for the development process. Another directory is the test directory that provides all the unit tests and feature tests there. And it also has standalone CMake file that can be used directly from this directory. And there is a wrapper, the top level wrapper that I said that can, for example, define those flags with warnings for you. And basically it's being used as an entry point for your IDE, for example, or for some compilation process. So basically this is the file I open in CLion or Visual Studio to develop the package. To not be forced to install stuff before I can test it, for example, during my development process. This entry point looks like this. This is a simple file that just adds subdirectory source and adds subdirectory test, and there is no magic here. As I said, it's being just used for IDEs I use for development. And this is how the unit testing CMake file looks like. Basically, you can find here, the important information here is this if branch. It says that if there is no target already known that's called my company, my library, it will find it with find package. Or otherwise, we reuse what it already knows. And it will know it only if this file is being run with this top level wrapper file that already imported the source directory earlier. Yes, here. So it imports source and then import tests. And this test then will know already about the target, will not use find package. If you will be running this test standalone from this directory, it will not know about my library, will use find package to install it or to get it from installation directory. So basically we compiled everything, built, verified if everything is okay, and we are done, yes, with our package. No, it's not right. It's asocial code, as David Senkel defined some time ago. We have to provide some installation interface and some things that will allow the users to reuse our library. We have to export our headers, we have to export our binaries, we have to provide CMake configuration files in order for others to be able to reuse our stuff that we develop so hard. So basically this is what we do. This is some brief of our CMake list file that we already analyzed. This is some summary of things that are there. And we have to install stuff. We have to say which targets are being installed. They are exported to my library targets, and it defines where those will end up in the file tree. And then we specify then where this my library targets, where they will be installed on the file system, and how the file will be called, and what will be the namespace used. Yes, this is exactly the same namespace we use for alias. I know there's a lot of boilerplate here, and unfortunately there is no simpler way to do it. At least for now. You also have to copy your public headers, and only public headers are needed there. And you have to provide the information about the version of your package that you are distributing. So you can use the package config helper to create this version file, and then you install it together with custom file called my library config that you can create easily with such a few lines. Okay, so the package flow that I'm using during the testing, as I said, I'm changing directory to my source directory and use this standalone CMake file in order to compile, build, and then install my library being developed. And then to verify if it can be imported by the users, I go to the test directory, and also CMake configuration step here is being done, and I run ctest to verify if it works correctly. Yes, so with this, I'm able to verify if the package is created and imported correctly. Okay, so this is about CMake. CMake, it turns out that's not the last tool in the toolchain that we have to use. It answers us the questions how to build project on many different systems, on many different compilers. It's good for it, but for distribution packages, it's not that good at all. Using this find package workflow that we already defined, we may have some problems. For example, let's consider that we will we'll have to recompile a new version of dependency low in the hierarchy. Then we'll have to recompile everything up in our project, yes? It doesn't scale if you have many dependencies, many configurations, and so on. And let's consider, for example, that you would like to verify every time you build your library, you would like to verify if it works correctly on GCC, Clang, Visual Studio, on both debug and release, and maybe with some custom flags for different builds, like, for example, if you are using exceptions or not, or you are using specific, I don't know, C++ version, 11, 14, 17. How do you install all of this stuff to your file system? Where are the directories you store it? How do you find them, those binaries in 16 different versions with find package later on? It doesn't scale at all. What we want is a package manager here. We would like to have one build process that builds all of the dependencies. It should rebuild the projects only if needed, if there is no binary needed and up to date for it. We shouldn't be forced to manually download anything from the internet, it should do it for us. And if there is something already installed on the file system, we are not forced to use it. For example, the boost that is there, we want to use different version of boost, for example. And these are the commonly asked features of package management for C++. However, when I started to work with Conan, I found out that I have requirements that I didn't know about earlier. It was exactly the same for me when I started to work with Git. I never thought that I will be able to go offline to my lab with a pen drive and do version control system there on my pen drive, yes? This is game changer, and it opened your eyes for new requirements. The same did Conan for me. These are the features that I right now require from package managers. I need decentralized servers, the same as Git. I need to have a server for open source. I need a server for my company private stuff. I need a server for my private stuff to play with. I want to have a central cache on my local PC of packages. So for example, if I have 10 or 20 different libraries that are using GTS or Boost, I don't want to store the sources and binaries in every subdirectory of those packages on my disk. I want to store this, if I'm compiling the same version with the same settings, I want to have only one binary on my file system. Otherwise, I will have enough on my SSD disk space for 3 projects only, talking about Boost, for example. I would like to have support to always compile my project from sources if needed for performance reasons. Because if you compile everything from sources, it's the fastest possible, but it takes time. If I want to spare some time, if I want to make it faster, I would like to use pre-built binaries if they are available, for CI, for example. And in some cases, you don't have sources at all. You have closed source libraries distributed only with binaries and headers. You have also some development tools like I don't know, CMake or NASM or other stuff that you don't have the sources for it. You just have binaries and you want to package them. The last point here that is really important for me that I found out is offline use. The same what I stated to Git. With Conan, I'm able to start a new project in a plane going to CppCon, and it works fine. And it will install and compile the GTest for me if needed, because it already has GTest sources in its cache. So it can work offline and work everywhere with it. It's a really nice feature. So talking about Conan. Conan is open source software with MIT license. It's decentralized, as you probably already noticed. Servers are dummy. They are not doing anything. They are just packet storage. All of the logic is stored in the client. The client is possible for packaging, for building, for installation stuff. It's portable to every platform that supports Python, and it uses Python as a scripting language. It works with any build system right now on the market, and it's easy to host. This is how you host packages. You have JFrog Artifactory, Conan server, and JFrog bin tray here. And this is our client. Client is a simple control terminal application. It is responsible for package creation and consumption. It also handles the local cache on your PC, as I said. It's really nice features and allows you to work offline. JFrog bin tray is the most common and most popular server with Conan packages. It's free for open source. And you need to create an account only there if you want to upload stuff. If you want to reuse stuff, you don't need an account there. Conan server is a simple, really simple TCP server of Conan, and I don't recommend you to use it. But what I recommend you to use in your company is JFrog Artifactory. That is a high-quality server, and basically with Community Edition, it's free to use, which is really nice. The most popular Conan repos on the bin tray is a Conan Center, Bin Crafters, and Conan Community. There you will find different packages already with a high quality, and you can start playing with them. To start playing with package, you have to know how the package identifier works in Conan, because it's quite complicated. It has package name, it has package version that's basically a string, but in most cases it's a number, but it's handled as a string and you can provide strings there. The user means who is the owner of the package. So for example, you may have your own Boost compilation on your servers, and it will just work fine. You may provide some different flags for it, or you may have some patches for it, and still it will be named Boost, but it will mean that it's Boost of your company, yes, with some patches, with some specific configuration used. It works really nice and it scales fine. And the last part here is a channel. It means what is the stage of the package you are using. If it's a stable or testing. And I mean here, this is a state of the packaging source code, not the packaged software itself, yes? So basically it's the Conan stuff, what is the state of it. Conan packages looks like this. This is on the server view. You have here information about the exports. You have here so-called recipe files, and you have one or more binary packages on the server. The binary packages are identified by this hash that is created from some specific settings and options. This is how it looks on your file system. It looks really the same. What's interesting part here is that you have, for example, only one hash here because I needed only one hash for my build. I don't download all the binaries from the server only to use them. If I need to use only one, yes? I'm downloading only this one. Conan do it by itself. It downloads only this one that's needed, and the rest stays on the server all the time. To search for a package on the server, use Conan search. Basically, Conan search without any options verifies what you have already in a local cache. But if you want to check on the remote, you provide the remote name. And for example, this will print all the gtest versions that are on Conan Center right now. This will provide the information about specific package. I will show you how it looks on this next slide. And this, for example, will create you the metrics of the binary packages available on the Bincrafter servers for gtest. This is how package information looks like. So basically, you can see here that there are some options used for the package, like for example, if it should be built with gmock or not, because it's a gtest, yes. And also there are some settings. Settings are operating system and build specific stuff, like which compiler was used for compilation, what was the architecture, is it a debug or release, for example. And all this information is available from the command line. You can also inspect the dependencies of the package with Conan info. With 2 dots, you will just refer to the Conan file and will verify your current project dependencies. You can verify dependencies of specific package. You can basically generate a graph of those dependencies. This is how this information looks like for dependencies. For example, for OpenSSL here, we have information that it uses zlib And then we have sleep information saying that is being required by OpenSSL. To install dependencies, you run Conan install command. When you will provide the package identifier and a generator, you can do it manually. But in most cases, we are using so-called recipe files. Recipe files are Conan file.txt and Conan file Python script. We can use profile files in order to say which configuration we are using for building. If you are building for Visual Studio, or we are building for GCC, or we are using debug or release, you can create as many profile files as needed. If profile file is not provided, then the special profile named default is being used for you. You can also say how to handle specific dependencies, if they should be built, if they are not exist, or not. Or it should be just Conan installation error saying that you don't have binaries for this package. This is how Conan file looks, this recipe file, yes? It has 3 stages: requires, options, generators here. Basically, CMake generator provides some CMake variables and functions, but there are generators for any build system you can use. We scope on CMake here because, as I said, CMake is the way to go for C++. This is the same file, but in a Python version. You can see that it provides exactly the same information as the text file. When you want to provide some options in those files, you can say, for example, that GTest will be built as a shared library, and this is the same in both files here. You can also override this from the command line, and you don't have to modify the recipe file. When you try to run shared libraries with Conan on any other build system, you will find out that probably you will have problems that your application doesn't find the binaries needed in order to execute your project. So for this, we have import command that imports the binaries to your local directory and makes it possible to find by the application that you are building. If you need more from Conan, you can still work with Python and extend it. For TXT file, you cannot do much more, but with Python, you can have more. For example, you can provide a build method that will say how you build your project. With that, you can then say only those 2 commands on your command line, saying that you want to install all the dependencies for Visual Studio 2017, and then build it. And you don't have to bother with CMake commands at all. Conan will build it for you based on this recipe provided in build method. You can also provide some options to your package, saying, for example, that if you set testing to true, you will be using some dependency in a testing version of it. We'll test 2.0. But however, if you will set it testing to false, which is a default, you will use a stable version of a dependency in your project. This is some additional logic in requirements method in your Conan recipe file. And there are many, many more features. We'll see a bit more later on. Conan profiles, I already mentioned them a bit. There is a default profile and the profiles you create by yourself. They have settings, options, environment variables, and build requires elements there. For example, this file looks like this, that you have information about the operating system you are using, or operating system that you are building for. This is used for cross-compilation. Which compiler you are using, which version, what is the version of the library you are using. Should it be a release or debug? For Visual Studio, you have also runtime version you are using. And for example, in environment variables here for Clang, you provide how to find Clang compiler on your file system. You can override easily any profile settings with -s option. And with this, it will reuse all of the options from Clang profile and use debug, yes, as a build type. Yeah, you can have profile files either in the default Conan directory for profiles, or you can store it together and distribute together with your projects. It's distributed here, and you can also include other profiles inside. Conan packages. When we create packages, we have a few options to consider here. First is that the package is created independent from the package project source code. So for example, you can create your own package source code to package Boost or package gtest and not have to modify the gtest code, yes? You create another repository that has only the packaging code there, and the gtest is another repository that you are using for packaging. So it's used for third-party libraries. And when you are packaging your own library, you have also two different options here. You can export all of the sources on the package servers, on the Conan servers together with your package, or you can still use the code from the repository like GitHub and only store the recipe on the Conan server. You can package existing binaries. So for example, in case when you have only pre-built binaries available for third parties, or you want to, or for example, you already created some expensive CI for your project and you have everything built on your disk and you don't want to rebuild everything from scratch to create a package. You just want to reuse what you already have, then you can use it. And the last point here is when you are packaging development tools. I assume that you are not compiling MinGW or Clang or other compilation tools every time you build your project, yes? So basically you use those binaries and you provide them also in Conan as a dependency. So you can install things like NASM, for example, together with OpenSSL package in order to make it compile from sources if needed. In the later stages of the presentation, we'll scope mostly on the point 1 here because it's the easiest one here, but others are really similar. So this is how such a package looks like. It has a Conan file recipe file, and it has license of your packaging content, not the packaged content, but your packaging, so what you write here. And it has test package directory that basically is a client of your application, and the configuration and installation parts are verified here. This is how such a recipe looks. You provide basically the package information. You provide the license of the package project. So what is the license for this Google benchmark stuff? Where to find it? Your source code for the packaging. Exports the license of your packaging software. So what's the packaging software, packaging code license? Which settings will be used to identify binaries. Each change in those settings will create a new binary in Conan. And also options. There's once again change in those will make a new package in Conan. This identifier, this hash will be different if you change any settings or any option here. You can provide also the defaults for those options, as you can see. And you can provide a new attribute called SCM, that is information where you store your package that will be packaged in your project. So where is the project being packaged? Important point here is to understand what is different between settings and options. Settings basically are the project-wide things, OS-specific things, compiler-specific things that are provided during compilation stage. And options are the things that user may provide, if he wants to build gtest with gmock or not, if he wants to enable, for example, exceptions or not in the project. And for this, you can provide default options. Other useful attributes in a recipe file will be generators. Basically, you would want to have generators if you have any dependencies in your software. However, you can also use them for setting some flags in CMake, for example. Requires will provide you the dependencies of your package. You can have private dependencies, for example, here. And you can also provide version ranges, but basically it's supported but not considered as a good practice, as you will learn later on. Other attributes that may be useful are build requires. These are the dependencies, but used only by the build process, and it's not being used by the clients. Exports will copy all the provided files to the package. Like, for example, you can export the license there. Export sources creates a snapshot of your sources. So this will be this point 2 in packaging scenarios. You can provide the homepage where people can find the project being packaged. And besides having attributes, there are also methods that can be used in Conan, a recipe file. Let's create such a helper method called configure CMake that will basically create a CMake helper here that will provide some definitions here and will run configure at the end. This CMake will be used later on by build and package methods, but it's important here to note that you may find that there's option shared that is not being set here for CMake, and this will modify this shared or static library flag that I mentioned earlier talking about CMake, and basically it's so common flag that Conan does it by itself in this helper, so you don't have to bother about it in your source code. Another important point here is that, for example, Google benchmark has testing set to on by default, and basically you don't have to pay for it every time you build your package from sources because you don't bother with it too often. And also it's not a good option to export this as a recipe options, because either way, if you will set up it to true or false, it will not modify the contents in the binary package that is being exported from Conan. But as I said, setting all different versions or setting different values for options will generate a different package ID, so different package for you. So basically you will export and distribute a separate package for building with testing or building without testing, but basically the contents will be the same, which is not too wise. So we have a build method here that basically takes this helper, creates CMake, and do CMake build. We have package that also configures CMake and makes install and copy the license to the package being distributed. And we have package info saying how the clients will link with our library. Where to find information with it, we say that it's a CMake benchmark target that stores all the information needed to link with this tool. Other useful methods are source. Basically, it will provide download the sources from Git, for example. It's being used mostly when you're not using this SCM attribute that I've shown you earlier. Requirements. So this provides more advanced logic for requires attribute. Build requirements is the same, but for building specific dependencies. Imports, as you've already seen in the shared library case, when you were importing the binaries in order to be found by the shared library. And package ID that defines how your hash is being created from settings. For example, you have specific configuration for header-only libraries here. You may have configure to specify how you configure the package, and restrict some options in some specific cases. For example, you may say that fpic is not available on Windows, and in such case, this package will not have this option for Windows setting. Test package directory basically provides you very simple package verification test. It is not unit testing, it is not feature testing, it's just mostly linking test in your Conan directory. This is how the recipe files for it will look. What we'll find here interesting is that it doesn't have any requires clause, any requires attribute, because Conan will provide the requires for you with the version you are creating right now, so you don't have to update it every time you are building a new version. To create a Conan package, you use Conan create method, command, let's say. And it will export the Conan file Python script and all the exports to the local cache. Then it will build and install the package. It will create a temporary directory in test package directory and will use install to download your library as a dependency and verify if it builds correctly. The same stuff once again. And at the bottom we have our local directory. In the upper part we have Conan local cache. When we are doing export or create, all of these things are being exported to the local cache. So we export the recipe and we export sources if export source attribute was provided. Then all of this is being copied to source directory, and then SCM attribute is being used to download the rest of the sources, or the source method is being called to do some logic, for example, to download the sources or maybe patch the sources, because you may apply some patches here, do some modifications to CMake files and so on. And then the sources are being copied to the binaries directories. It's being done because sometimes during the build phase you modify the sources and you don't want to have it in a global source directory that is being used by all the builds here. And then you build it with build method. After that, when the build finishes correctly, we have package method being run that basically copies everything to the package directory, install stuff, and this is what you distribute to the bin tray server later on. When you run Conan install, it will import all of the binaries and will create some stuff with generators. When you are developing a package, you may use this development flow in Conan. So you start with Conan create user channel. If you find out that the source is created correctly, but something else later on fails, you may run it again with keep source, so will not pay for this stage again. You will start from this point. When you find that it builds correctly, you may say keep build and just verify if its packages correctly or unit tests are being run. You can rerun the tests with this command if needed. You may have also even better granularity with those commands. So basically, you may only run sources or installation process or build process or packaging process or testing process with it. Or even you may have even more granularity with additional options for build, that's configure, build, and install. These are mostly the CMake steps here, being done during build phase. What does it mean to distribute a good quality package in Conan? Basically, your Conan recipe file should have a description, name, license, and some hyperlink to your home pages, to licenses, and so on. It should use lowercase letters for package names. It should have test package that will verify if your package compiles fine. It should raise errors on every invalid configuration. It shouldn't use version ranges because there are some problems, especially performance problems with it. It should package both the license of the project you are packaging and also your license as a package author. And you should use the clean Python and the latest features of Conan because they are helping a lot. If you are done with package creation, you probably want to share it somehow with others. For that, you add some remote to your Conan with such a command, for example, for bin tray. And when you have remote added, you upload it with upload command. -all here means that you are uploading all of the binaries being created in your local cache to the bin tray. And you are done basically with it. That's all about the Conan. You have to know in order to create packages. We'll scope right now more on the cooperation of Conan and CMake. So we have 4 generators being used for CMake. CMake, CMake Multi, CMake Paths, and CMake Find Package. CMake is a basic generator. This is the oldest one. It creates Conan built-in for CMake script that keeps variables and some helper functions there. In order to run them, you have to run Conan basic setup co. And this is how you do it. You have to modify CMake list file in order to run those commands here. Targets means that you are using target versions, so modern CMake is being used instead of the old CMake. So if you not provide targets, old CMake style is being used. I recommend you using this if branch here, so it's not, it will compile if you are using CMake with find package, or you will provide GTS root or other variables to find packages, and it will not force you to use Conan all the time. Yes, it's optional for use right now. Conan is not a standard yet. Not everyone is using it. You shouldn't force end users to use Conan right now. Maybe in 5 years, when everybody will have Conan maybe on their development platform, then this if branch will not be needed here. But for now, it's an option, not a must. CMake multi-generator is the one used for example, for Visual Studio. It doesn't specify if you are using debug or release during the configuration phase. It's being specified later on. It has some problems with it. It cannot be used for package creations. It will make find package in CMake not working correctly because it will not know if it has to find information for debug or release, for example. So basically, I don't recommend using that one. The new generators in Conan are CMake paths and CMake, I don't remember the next one, find package. Basically, this CMake paths create the CMake path CMake script that has only 2 variables there. CMake module path needed by find package and CMake prefix path needed by find library. In order to use it, you can either set only this one line in your CMake script, or you can even use it without any modification of CMake files with specific CMake define, CMake project include with your project name here. And in that case, it's not intrusive. You don't have to modify CMake files at all. CMake find package generator will create your find CMake scripts, and it's possible to also to use without any changes to the CMake. When using with Python script, when using with txt file, you may have to modify CMake file or use this together with CMake paths. At the end, we have only 3 minutes left. I would like to share you some BKMs I found during the package creation. So this is how you can automate CMake file modifications, so you don't have to do it manually. Basically, you can use the tools helper here and replace the line saying project my library with project my library and in this Conan information inclusion code. Or you can do it in another way. You can download all the sources to subfolder and export some small CMake list file. That's the source you have here. So basically, it's a wrapper that does Conan specific stuff and runs the CMake from subdirectory source folder, yes? If you want to run unit tests during your build phases, you may use Conan run tests environment variable. There are some additional helper methods used here, like build requirements that will specify some logic for requirements during the build phase. You provide some definitions, and you use CMake test in build step, and if this variable is set. And in order to use it, you either modify environment variable, or you provide this in a profile file, or you run this command with -e. You can also provide custom find CMake scripts with your package. This is in case if the package that you are packaging is asocial, so it doesn't provide any installation directories and installation information with it, or maybe the file that's being created, it looks, for example, always in C/directory in Windows, yes? So basically, it will not work with Conan. And for this, you just create your new find CMake file, and you make export sources for it, and then copy it with package to the place where package is being stored, and it will be found by the CMake later on. The last BKM I wanted to share with you is do not use the class attributes, class variables to share state. It will work fine when you are running the Conan create function, because this command will run all of the member functions of the CMake. However, if you would like to repeat some steps only, like for example, run Conan package command, this will run only this function, and this function will not set those variables because those variables are being set only in source. Yes, so it will not work for you. So that's all. As a summary, CMake. Many projects do not use CMake still. I would recommend them to start using it because it's a standard on the market. If they are using CMake, sometimes they don't use modern style of CMake. As you can see, that gives a lot of benefits for you. So I recommend strongly using modern CMake there. And be social, yes? For Conan, I found it to be a production quality package manager. It's designed with C++ in mind. So it works for us really good. It's for free. MIT license, server is also for free. It's quite easy to use if you understand this flow and how these packages, what are the steps in the process, and all of this is really well documented. So there are like 400 papers, 400 pages in the documentation regarding CMake. So it's Conan. So it's like a Conan documentation for free, a book for it. So give it a try. With that, it seems I'm out of the time right now. So thank you everyone for coming. I can answer the questions during the break later on, but probably we should stop the recording right now. Thank you very much.